Welcome back to another explainer. I am so incredibly pumped you're here today because honestly, we're looking at something just absolutely awe-inspiring. Have you ever just stood outside, looked up, and thought about the sheer mind-boggling scale of the sky? I don't just mean a few passing clouds or a rainstorm. I mean the entire atmosphere. Today, we're zooming out. We're going to look at the Earth not just as our home planet, but as this massive, impossibly intricate heat engine. We're literally going to pop the hood and decode the brilliant mechanics that keep our global atmosphere churning day in and day out.
So think about this for a second. What invisible engine drives every single storm, every gentle breeze, and every commercial flight path on the planet? It's so easy to walk outside, feel a sudden gust of wind, and just write it off as some random localized event. But actually, that breeze hitting your face is just one tiny interconnected moving part of a gigantic, globally coordinated machine. Okay, so here's our roadmap for understanding how this engine actually works. We'll start with our solar fuel, which is insolation. Then we'll balance the Earth's heat budget. From there, we're diving into global pressure belts, the winds of the world, and finally, the ultimate high-altitude highways, the mighty jet streams. Let's get right into it. Part 1. Solar fuel, insolation. The technical term for our engine's fuel is insolation. That's basically the incoming heat and light we receive through space directly from the sun. And to actually measure how intense this energy is, scientists use a unit called Langleys. Think of this incoming heat as the literal, physical fuel that powers absolutely every atmospheric process we're going to talk about today. It all starts right here.
But here's the catch, and it's a big one. This solar fuel is not distributed equally, which is actually a great thing, because if it were, our planet's climate would be incredibly boring. A whole bunch of factors mess with how this heat gets handed out. You've got the Earth's rotation and its 66.5-degree tilt, which means the sun's rays hit different places at totally different angles. A direct overhead ray is going to pack a serious punch of concentrated heat, while an oblique, slanted ray gets spread out and loses a lot of juice traveling through more of the atmosphere. Then add in the fact that our orbit isn't a perfect circle. We actually grab slightly more insolation when we're closest to the sun during our revolution. Throw in varying lengths of summer days, topographic slopes, atmospheric blockers like clouds, and even the 11-year sunspot cycle, and what you get is a wildly, beautifully uneven distribution of energy across the globe.
Now, this uneven distribution creates a pretty wildly counterintuitive reality. You'd naturally think the equator, being right smack in the middle, would get the absolute hottest, most direct solar fuel, right? But actually, maximum insolation hits the subtropical deserts. Why? Well, it's all about atmospheric transparency. The equator has a massive, thick layer of constant cloud cover that physically blocks the sun. Meanwhile, those dry subtropical deserts, they've got totally clear, unobstructed skies just soaking up all those long lays all day long.
Which brings us to Part 2, Earth's heat budget.
Think of the heat budget exactly like a financial accounting ledger. It is this incredibly delicate planetary scale balancing act between the incoming energy we gain and the outgoing energy we lose. And a massive player in this budget is a concept called albedo. Albedo is simply a measure of how much radiation a surface reflects. Different surfaces process heat very differently. For instance, fresh snow or thick ice has a super high albedo. It acts exactly like a giant mirror, bouncing a ton of that incoming insolation straight back into space. On the flip side, dark surfaces, like a deep ocean or a sandy beach, absorb that heat, holding onto it and essentially baking the air right above it. Normally, as you climb higher up into the atmosphere, the air gets cooler. This is called the normal lapse rate. Basically, the temperature drops about 6.5 degrees Celsius for every 1,000 meters you go up. But sometimes the accounting gets totally flipped in this fascinating phenomenon called a temperature inversion. Imagine a long, crystal clear, totally calm winter night. The ground loses its heat incredibly fast, meaning the bottom layer of air gets freezing cold, while the air sitting just above it stays relatively warm. That warmer air acts literally like a lid on a pot, trapping all the dense, freezing air and fog right down in the valleys. This is exactly why if you go to mountainous regions, you'll see entire villages built up on the slopes rather than down on the valley floor. They are quite literally climbing out of a cold air trap.
Moving on to Part 3, global pressure belts.
Okay, so this is absolutely crucial. If you remember one thing, make it this 3-step domino effect, because it's essentially the core equation of all weather. Step 1, that varied insolation we just talked about creates uneven heating. Step 2, that temperature difference physically alters the density of the air. Hot air expands, gets light, and creates low pressure.
Cold air compresses, gets heavy, and creates high pressure. Step 3, our atmosphere absolutely hates imbalance. It despises it. So that heavy, high-pressure air forcefully rushes in to fill the empty space left by the rising low-pressure air. And that horizontal movement of air, that, my friends, is wind.
Because of this never-ending hot and cold balancing act, the Earth has developed these permanent global pressure belts. Right at the equator, hot air is constantly rising, giving us the equatorial low. You might know it as the doldrums or the intertropical convergence zone. As that rising air moves toward the poles, it cools down and sinks right around 30 degrees latitude, creating the subtropical high. Sailors famously call this dead zone the horse latitudes. Further up, you've got the subpolar low, where different winds smash together. And finally, capping it all off, the freezing, incredibly dense polar highs. And here is the really cool part. Because the Earth is tilted, these belts are not painted on. They actually physically swing north and south throughout the year, perfectly following the apparent migration of the sun.
But here's the thing. Air doesn't just travel in a nice, neat, straight line from high to low pressure. Why? Because our giant engine is spinning. Enter the Coriolis force. Because the Earth is constantly rotating, it physically bends these massive wind currents. If you're in the northern hemisphere, winds get deflected to their right. Down in the southern hemisphere, they get shoved to their left. Interestingly enough, this rotational bending force is exactly 0 at the equator, and it gets stronger and stronger the closer you get to the poles. It's really the ultimate governor of how air moves across our world.
Let's see what that looks like in part 4, Winds of the World.
All that pressure and spinning gives birth to our major planetary winds, which are governed by these absolutely massive circulation systems like the Hadley and Farrell cells. Between the subtropics and the equator, you've got the super reliable trade winds, constantly rushing in and converging at the equator. Head into the mid-latitudes, and we hit the westerlies. And I've got to highlight this because it's wild. In the southern hemisphere, there's hardly any landmass to create friction and slow the wind down. Because of that, these southern westerlies become absolute monsters. Sailors legitimately call them the roaring 40s, the furious 50s, and the screaming 60s because they are just that intense. Finally, blasting outward from the extreme poles, we have the freezing polar easterlies.
But hey, we don't just feel global planetary winds on our faces, right? This engine operates on a local level too. If you've ever lived near the coast, you absolutely know the sea breeze. During the day, the land heats up way faster than the ocean water. That creates a low-pressure vacuum over the land, which aggressively pulls in cool, refreshing air from the sea. At night, the land cools off faster and the whole system throws it in reverse. We see the exact same mechanics up in the mountains. During the day, the air in the valley heats up and flows up the slopes. But at night, you get a mountain breeze, often called a katabatic wind, where heavy, dense, freezing air comes literally rushing down into the valleys below. And this brilliantly shows how our planet's very local topography interacts with the global engine to create some incredibly specific and famous local winds. Take the Lu, for example. It's this punishingly hot, dry wind that sweeps across the northern plains of India. Over in the US and Canadian Rockies, you've got the Chinook, which is another hot, dry wind. But jump over to Europe, and the Alps are busy generating the Mistral, a bitterly cold, completely dry wind that just blasts down toward the Mediterranean. And of course, way down in the Antarctica, you have the ultimate freezing force, the blizzard. Almost every region's unique climate is stamped by these specialized local exhausts.
Which brings us to our final act, part 5, the mighty jet streams.
So what exactly is a jet stream? We define it as a highly concentrated band of extremely rapid air movement located way up near the top of the troposphere. Let's be clear, these are not your everyday fly-a-kite surface breezes. They are massive, totally invisible rivers of air flowing far above our heads. And they don't flow in a perfect, rigid circle either. They follow this wavy, meandering, snake-like path wrapping around the globe, which scientists call Rossby waves. To fully grasp the sheer scale and power of these high-altitude rivers, just think about this number. During the winter months, when the temperature differences between the poles and the equator are at their absolute most extreme, the jet streams can accelerate to a staggering 180 kilometers per hour. That is mind-blowing. Even in the dead of summer, they're still racing along at a casual 110 kilometers per hour. The dead center of these circular bands packs a frankly unbelievable amount of kinetic energy. So why does an invisible river of air miles above our heads actually matter to you and me down here on the ground? Well, because the jet stream basically pulls the strings of all our surface weather.
It single-handedly dictates the paths of weather systems, deep cyclones, and massive storms. In fact, a very specific seasonal current called the Eastern Tropical Jet Stream is directly responsible for the sudden, dramatic bursting of the vital monsoon rains over India. And on a very practical, everyday level, if you've ever noticed that a flight from New York to London takes significantly less time than the flight back, it's because commercial airplanes purposely hitch a ride right inside these 180-kilometer-per-hour jet streams, saving massive amounts of time and millions of gallons of aviation fuel. When you step back and look at it, from a single ray of insulation hitting the Earth, to the vast pressure belt swinging across the continents, to the screaming westerlies and the high-speed jet streams way up in the upper atmosphere, it's all one beautifully designed, perfectly continuous engine. Everything is connected. So I'm going to leave you with this. The very next time you hear the wind howling outside your house, stop and ask yourself, which part of Earth's massive heat engine is blowing past your window right now? Thanks so much for joining me on this explainer. Keep observing the amazing world around you, and I will see you in the next one.